Okay, well, welcome to another section, quantum hardware. Today we start a new model, the quantum, the optical cavity, quantum electrodynamics. So we see some application of quantum electrodynamics. And today I'm planning to give just a summary of the brief ideas behind the quantization of the electromagnetic field. And in the next, because in the in the book he just give the expression, so I think it's important we discuss, even if we don't see all the details because we will get too long, but we can in 1 hour discuss something. But I will start because I think the last time when we finish the the quantum optic models, I forget to tell a little bit about the drawbacks about our model. So I'll discuss today in the beginning, and then we start the, the other topic. So okay, let's see here. Okay, this is still a nonlinear Kerr media optical photon quantum computer. I just forget in the last section to discuss a little bit about the drawbacks. When we finish. And just to say, it's basically what is in the Nielsen book. So the single photon representation that we consider in the past lectures is attractive for qubit representation because we're using photons, right? And for the fact that single photons are relatively simple to generate and measure. In the dual rail representation, arbitrary single qubit operations are possible, as we saw. We could at least theoretically manage how to do some important gates like C0 gates or a Fredkin gate and so on. But the problem is that interacting photons is not easy. In fact, it's difficult. Like in the vacuum, photons do not interact, right? But so you need a medium to make this interaction. In the case that we were considering was like the photon interacting with the nonlinear medium, the atoms in the nonlinear medium, and the atom interact with the photon. This we call cross-phase modulation, right? And we consider the medium we consider nonlinear medium or Kerr medium. And the best Kerr medium available in general are very weak. Remember that when we talk about Kerr medium, we are considered central symmetric materials, where the highest susceptibility factor is the chi to the 3. So in general, this is very weak. So to make these photons to interact, I think in general we will have a good material. We will have something like 50 tries. We will have one that could work, something like that. And the problem that the other photons would be just absorbable by the material and could not interact one with another. So with this, which is a big problem, for the optical models, the photonic models in general, that's the interaction of the photons. It's not easy. We have another issues. Like for studying this optical quantum computer that we consider, we have gained some valuable insights into the nature of the architecture and the system design for of our quantum computing. We now can see what an actual quantum computing constructed nearly completely from optical interferometers, like we consider like the exercise we made in the last lecture, must look like in the lab. However, it would be challenging to stabilize this type of devices when dealing with large quantum algorithms. Remember that we considered like the Dutch algorithm in the last lecture, and we consider only 2 qubits, right? And we have like that circuit, but if we increase the number of qubits, you you would have a more complicated algorithm, and the 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 number of optical devices that was like could be need to to make these algorithms like to work would be much bigger, and this would not easy like in the lab to stabilize the, the these optical devices. And despite these drawbacks, the theoretical formalism which we described these optical quantum computers is fundamental in all the realizations that we will study in the future. Particularly that we studied like today, which is the optical cavity quantum electrodynamic computers. This is just another kind of optical quantum computing, but with different a kind of nonlinear medium that we will discuss with more details in the next Friday. So okay, so this is just I forget like to comment in the last lecture, but so basically the main problem from the optical models that we consider are how to make good interaction between the photons. It's not easy uh, experimentally, right, in the lab, because the nonlinear Kerr media usually are weak. This interaction is weak, and it's the type of things that we cannot like control. So for today, we are considering this other model, like the optical cavity quantum electrodynamics, QED for short. And we will study this new model based in optical devices. And so many of the things that we learned in the I think in the last month, will be useful here. And we use it like quantum electrodynamics. So today I'm planning just to give a short like review, summary about how to quantize the electromagnetic field. We did this when we were like talking about the coherent models, but I mean it was very short. I mean, because the idea there was not uh, just a motivation to have like this type of uh, model that we consider in the beginning. That's the coherent lasers using like the coherent modes. So we will see some advantage related to the previous models and the importance of the previous knowledge we learned, which we will apply here. So this model seems to be more efficient than the previous one, and we'll see like during this month, March. I think till the end of March or early April, we finish this about this model to talk about the main thing. So cavity quantum electrodynamics is a field of study that accesses an important regime involving the coupling of single atoms to only a few optical modes. Experimentally, this is made possible by placing single atoms in optical cavities. And the cavity that we will study in the next in the next lecture is called like Fabry-Peyroux cavity. That basically it increases the intensity of the field when you consider like two mirrors, like in parallel, and you let the photons back bouncing back and forth in this medium, like in the cavity. But this we will see in the next slide. So, because only one of two electromagnetic modes exists within the cavity, and each of these has a very high electric field strength, the dipole coupling between the atom and the field is very high. Because of that, photons within the cavity have an opportunity to interact many times with the atoms before escaping. So if you put some atoms, like few atoms, could be like a single atom as well, in the cavity, the photons will interact with this cavity while it's like making like a round trip, like bouncing back and forth in between the the mirrors. So theoretically, this technique presents an opportunity to control single quantum systems, in particular quantum computers, which are the systems that we are interested in. The single atom cavity quantum electrodynamic method offers a potential solution to the main problem related to optical quantum computing described in the previous lectures. That is, like when there are single photons, which is a good carriers of quantum information, but they require some other medium. It's the K medium to interact with each other, as we discussed, right? And because nonlinear optical Kerr media are compounded by a large number of atoms or molecules, with the problem with the media be very small, I mean the susceptibilities be very small, and they has weak interaction, you still have this problem. That's the number of atoms and molecules that compound the media. And they are not good to satisfy the need to photons to be good carriers of quantum information, because they can, all these atoms that compound the Kerr media, it could like generate decoherence. And that's the problem, that so many you lose, like many of these photons will be like absorbed by the material instead of be like make this carry this information, like interacting with the atoms, and the atom interact with the other photons, and have information be passed from one to the other. So it would be much easier if your material has only single photons, only single atoms, sorry, and would be much easier to control, which is the idea here in this case. And because you don't have the material as well, you have like a cavity with some single atoms inside. So in this context, well-isolated single atoms might not necessarily suffer from the same decoherence effects that happens here in the Kerr media. Moreover, this could also provide cross-phase modulation between the photons. That is important. That's the cross-phase modulation, this type of model that makes the photons interact. And thus the idea is to transfer the state of single photons to single atoms with a controlled interaction. Okay, so the two main experimental components of the cavity quantum electrodynamic system are the electromagnetic field and the atom. So the main interaction involved in the cavity 3D is the dipolar interaction between the dipole moment D and the electric field E. So how large can be this interaction? That's in fact, this will be answered in the next lecture. This is just to give a beginning here. It's difficult in practice to change the size of the dipole moment. However, the electric field is experimentally accessible. And one of the most important tools for realizing a very large electric field in a narrow band of frequencies and a small volume of space is the Fabry-Pérot cavity. And in the approximation that the electric field is monochromatic and occupies a single spatial mode, it can be described for a very simple quantum mechanical description. Okay, so the book he just gives now the expression for the quantized electric field. So let's discuss the lecture today is exactly to discuss at least the main steps and how we could like quantize the electric field. Okay, and then the next lecture we apply this to the Fabry-Pérot cavity, and then we can like try to do computation. Okay, so questions, comments? No? I will write the electromagnetic field, but in fact, I will show only the electrical part. Okay, that is what we are interested. The magnetic part will be in similar way. So, okay, and I will consider here some, when doing this, I will just like using some parts of the classical electrodynamics. I will consider like that we already know the classical part, but if have any doubt about, you guys can ask as well, because otherwise it will be like to review everything will be too much thing. So the thing I'll planning to do, I'll do something similar that the lecture about like the care media. So I'll show only some parts, some important steps to do the quantization. Okay, so we'll not get into much details. Otherwise, it would be like a too long lecture. So let's put some steps here. The electromagnetic field. Magnetic field is quantized. It's quantized by the association of the quantum mechanical harmonic oscillator. And as well, I will use, just to give the reference, I'm considering this book here, like The Quantum Theory of Light by London. It's part of the chapter 4, I think. He do this. So, but you guys can find in other books how to do this, because it has a good description as well of the Fabry-Pérot cavity, and like to use like his in the next lecture. I will use this book again, so this part of the quantization of the electromagnetic field I consider to use like in the same reference. So, but I mean, you guys can, if you guys have another book, can find it's good as well. So in the Nielsen Schwenk, he used like a monochromatic electromagnetic field. But my idea here, I'll try to give like a more general idea for like a field with different modes and polarization, quantize, and then we go to the monochromatic that is more simple version. Okay, that's the expression 756 from the Nielsen Schwann book. So I'll be more. I'll make the quantization more general than that's we have in the book, in the Nielsen Schwann book. So, okay, the electromagnetic field is quantized by the association of the quantum mechanical harmonic oscillator with each mode k of lambda of the radiation field. In a cavity. In the cavity. So the modes, again, in the Nielsen Schwann book, because it's monochromatic, so we have only one type of mode. So we don't need to worry about that. But I'll give a general review, more general. So the modes to which the quantum mechanical operators refer are indicated by the subscripts. Okay. Okay. So just to remember when we would consider the harmonic oscillator operators like the creation and annihilation operator, we have the annihilation operator for the harmonic oscillator, just given by when applied to a state n, number state n, we have this relation. For n, for a, the annihilation operator, the creation operator, relation step. So in the case of this for the harmonic oscillators, no? Harmonic oscillator. For the electromagnetic field, see, each mode will have one description similar. So the destruction or the annihilation that we are using, our nomenclature, the annihilation and creation operators for a cavity mode like K lambda takes similar form. So each mode will have the annihilation operator that will be applied to this is in general is a vector, okay? In general, nk of lambda for this for each mode you have this. The same for the creation operator. So this one, the state. So the physical interpretation here the physical interpretation now physical interpretation now is that the operators destroy or create one photon. That's the radiation of the electromagnetic field. Right? One photon of energy is the same that the energy is associated with the harmonic oscillator, so is h bar omega in the mode k lambda. Okay, so k here is just the wave vector. Okay, that define k wave vector, and lambda here is you can write in the way you want, like 1, 2, because it is related with the polarization. Is the polarization index. So the wave could be like propagating, remember, the electric wave could be propagating on the right direction. It could be polarized, like perpendicular to the propagation, the direction of propagation. But this could be polarized like in this way, like in the vertical or in the horizontal. So the 1 or 2 here is the direction of the polarization. So it could be perpendicular to the plane propagation, or it would be perpendicular but inside the plane. Okay. So and n here in this case, like in the case of harmonic oscillator, we call like n just like a particle that's be creating. Here, nk is the photons excited in the cavity. Okay, in each photon with each mode, and each mode with the respective polarization. The definition of n similar to what we did in the harmonic oscillator case. So in terms of the creation and annihilation operators. So, and I think we use this. I think in our notation we call it like big N, cap N. So N applied to the state K lambda A K lambda as the N, the photon. Okay. And now this guy here that we call in the case of harmonic oscillator just the number state, they are orthogonal, orthonormal eigenstates, and are known as photon number states or Fock states. Okay. Okay, and each one, so because the modes are independent, so let's put here the cavity modes are independent and they associate operators commute. So we could write this like for each mode, A K lambda, A dagger K lambda. Could write this in terms of delta of K lambda K prime. Okay. So if you have the same mode, this is 1. But if it's different modes, so it's the commute is 0. Okay, so this is, I think is the basic. And we could like remember that in the case of harmonic oscillator, we just make like A dagger equal to 1. Right? And because they are in this case they are in the same mode, right? When K is the same of K prime here. So K and K prime and lambda prime. Because it could be in the same mode, but the polarization could be different. But when we have the same modes, the same polarization, so they do not commute. That's the usual when we have like the harmonic oscillator. So okay, and now we could like make a relation between the Hamiltonian on the system, on this system to the Hamiltonian, to the energy for the classical radiative energy to the classical field. So uh, just to remember the Hamiltonian from the harmonic oscillator. So again, but here the harmonic oscillator, we have a Hamiltonian going given by that. Delta A plus 1. That's the Hamiltonian. Okay, and this is the energy H bar omega. So the vacuum energy is just in H bar omega over 2. And okay, just to show we could write this simple just because I'll make a relation with the field. But we could write H better. Let's write this Hamiltonian in a more appropriate form. Just because when I have the relation with the classical energy, radiative energy of the electromagnetic field, it will be much easier to identify the terms if I change this notation. So we understand this. So let's write this Hamiltonian in a more appropriate form. So remember that A dagger is equal to 1. So I could write A dagger minus A dagger A equal to 1. And I'll like 1.5 if I divide both sides by 2. So I have 1.5 A dagger minus 1.5 dagger. Okay, so if I use this here, I'll find H bar omega dagger A plus 1.5 A dagger minus 1.5 A dagger A, which gives, could write this in this way, minus A dagger A, yeah, plus A dagger A. Okay, and then now let's associate. Let's define a similar Hamiltonian for each mode in the cavity. So I'll define a Hamiltonian, K of lambda. I will use this notation. 1.5 H bar omega, omega for each mode, okay? Okay. a lambda dagger a lambda plus a lambda lambda. Okay, and I can make, remember the Hamiltonian is energy of the system. So I could uh, let's associate this Hamiltonian with the radiative energy on the electromagnetic field. So in the classical theory, you could prove that this so-called E for each mole is given in terms of changes for epsilon 0 V omega k square. So in terms of the potential modes coefficients, I will define these things. So plus this is the classical theory. So this is just a complex conjugate of A. You could write in this way. Okay? Where A, K, lambda, just moles coefficients, which are associated with the potential vector, the electric field. V, this V here, is just the volume, the cavity, a cavity of size. If a cubic cavity, for instance, you could, and each arrestor is like L, so V would be L to the Q. Okay? But let's give in general. So V is just the volume of the cavity. This omega k is just the velocity of light times the each mode. Okay, it's this angular frequency. Let's see. And c is the velocity of light in the vacuum that is given in terms of the susceptibility is 0 mu is 0. This is 0 here. It's just the electric permittivity. The vacuum. Better call the free space, right? Because we are in the vacuum that we have in the cavity, in the free space. because the boundary conditions is different when we're solving this classically, when we are in a free space and when we have boundaries. And mu0 is the magnetic permittivity in free space. And C is the velocity of light. Okay. Okay, so we could make like the comparison of this guy here with the, remember, this is the energy per mode of the electromagnetic field, could be written this way. And we could have the comparison with the Hamiltonian. The Hamiltonian for the that we define for the electromagnetic field in terms of the similar that we had made before for the harmonic oscillator. So comparing the equations for H, K lambda, and E lambda, we could may note that we could just like compare the terms, since like both is energy, right? But one is classical and the other is the Hamiltonian is the quantum, because it's in terms of the operator. So the Hamiltonian, I have the operator, and the other I have the classical. So I'll make the relation between both. So if you compare the terms, we would find like, change the color. E0 V omega K square lambda A conjugate K lambda would be related with H bar omega K AK K lambda AK that. And the same for the other part, right? So we'll have this relation and that relation. So E0 V omega K square conjugate lambda A K lambda with H bar omega K lambda K lambda. And in doing this, we will just find, we could write like A K. So these modes here now are defined in terms of operators. So they are operators. So let's just put the hat here. It's operators, these operators. So this was like classical in the beginning, when we make this association between this operator and this classical term. So these guys are our operators. So we will have AK lambda associate within. If you make like these relations here and solve these equations, simple. You just have like H bar to omega K V epsilon 0. K. Times A K lambda. And the other, the conjugate, the same thing. Okay, V epsilon 0. Sorry, and notation here, this is this guy here. Epsilon 0. Epsilon 0. Okay. So we have this. And so with this association, with this relations, I mean, is better, right? With these relations, we can define the classical vector potential in terms of A K lambda A dagger K. So classically, A is defined this way. So A, if we are like consider the Maxwell equations, we put these boundary conditions associated with these boundaries, and we could find this in terms of A, K lambda, exponential minus omega t plus I K L plus I omega K. It's the conjugate of this, right? Minus I K. You could write this. So this is from the classical theory. So with the relations, we can define the classical vector potential in terms of this. So again, the classical potential, but this is the, just to remind this, to each mode, like the potential vector A K, we will not use this, just to RT, are just the sum of K in lambda, K, the sum of K lambda, well, lambda could be 1 or 2, okay? In terms of unitary vector, E A lambda A lambda RT. So this guy here, this guy, at the amplitude of the wave. So this in the Maxwell equations, you make the substitutions, solve the Maxwell equations, we'll find this solution in terms of this. So this is classical. Classical. Okay, now what we do, we associate this guy here, a k lambda RT will be operator in terms of the relation that we found before. So we associate these amplitudes here with the Hamiltonian of the system, and we found a given in terms of the annihilation and creation operators. So if you do that, oops, if you do that, you find we will find that A k lambda RT will be just h1 to omega k v is 0 times a lambda exponential minus I omega k t minus I k r plus k lambda dagger I omega k t minus I k r plus, no, plus here and minus. Okay, and we have like this expression, and we can find like the transverse field in terms of the potential vector. Like in the classical case, if we want to find like the electric field, the transverse electric field will be just the derivation of this vector. Okay. So here we do like the same. Let's make simple this, the quantized electric field. Let's use quantum. For each mode is given just by the derivation ddt. So just need to derive, make the derivation this in terms of t, and we will find this I omega k, a exponential minus I omega kt plus I k r plus, sorry, this is small a, right? This, okay, lambda. Okay, electric field, like in the quantum case, I'll just make the derivative of this for the transverse field. This plus minus here. So this in the vector. These are the like the in terms of the amplitudes. So in terms of the et just become e. I'll use the notation of the Nielsen shrine. So this is the sum of all modes. So classically, this is just the sum k lambda, the potential vector, not the unity vector, I omega k, and all these things here, right? I omega k. Oh, I forgot this. I forgot this term. Sorry. So this could have this guy. H bar 2 omega k v epsilon 0. Okay, this guy is here. That's this guy here. So here is the other terms, but this H bar 2 omega k v epsilon 0. Times all these things. Okay, ak lambda exponential minus omega k plus I minus I dagger exponential I omega kt minus I r. Okay. Okay, and this is almost the equation Nielsen 756, apart that he is considered like a monochromatic mode. So only one mode. So we don't need this for a monochromatic mode. We don't need this sum. We don't need this sum. And you can write E. E as the potential vector I here. This E here, he called just epsilon vector, and he called E0. We will identify the terms. A. So I have only one mode, so I don't need to write in terms of K. So A exponential minus I omega plus I omega t, right? I'm forgetting the t here. Omega t, omega t plus I k scalar r minus I delta I omega k t minus. And to simplify the things, we just consider that omega t is some multiple of 2 pi n, right? To be, let's see, you write this I epsilon E0 A exponential, where he is not with the, it's not time dependent, so it could be considered like the initial case, t equal to 0, or multiples of 2 pi. Okay, so exponential I k r minus a dagger exponential minus I k scalar r. Yes. So this expression, and in this case, he doesn't say anything about who is E0, but E0 is just this term here, right? What we are calling E0 is just this guy here. So let's see if I put this someplace. Yeah, E0 is just this H bar omega 2 epsilon 0 B. Okay, so this is the expression 756. Yeah. Okay, but this is just the field strength. Yeah. So, okay, guys, questions? Many questions? Yeah, this is the idea, just to give like how, at least the summary, how to get this equation 756. At least the quantum part, I think I make all the steps. I ignore a little bit the classical part. I didn't show the details, but I mean, if you guys have questions, we could like do now. I think today is this, and in the next Friday we will apply this to the fabric parallel. First, we will understand a little bit about this type of interferometer. That's the fabric parallel, very important. Like in producing lasers, it's using a lot. But we'll use here to try to make computation, a better way to make computation using optical devices. It's better than consider like the Kerr medium. But yeah, if you have questions, if not, I will stop the recording and we can have the discussion after. No? So, okay, I'll just stop recording. So next Friday, people from YouTube, we will study like the box 7.5 in the Nielsen Schwenk book and try to understand like the fabric pair or cavity. We apply these things that we learned today to this type of, of cavity. Okay, so let's stop recording.
Thank you, Carlos.
Okay, thanks, George. It's a little bit fast, I know, but I mean, we can discuss more during the other lectures, the things that we discussed today. So just to finish the recording.